Hello, everybody. Ladies and gentlemen, distinguished speakers, and esteemed participants, a warm welcome to the Decarbonization Business Starters webinar series, Decarb December. Decarb December is a learning series on thought to action in decarbonization. A short intro on Decarbonization Business Charter. The Decarbonization Business Charter was conceived to establish a unified platform that brings together key stakeholders, fostering collaboration for the decarbonization of the building and construction sector. This initiative is a collaborative effort between World Resource Institute, WRI India, Alliance for an Energy Efficient Economy, AEEE, Mahindra Lifespace Developers Limited, and EcoCollab. It aims to address shared challenges and opportunities. The Charter provides a framework to identify and prioritize critical actions, steering efforts towards the common goal of reducing carbon emissions in the sector. Over the next few days, we will have the privilege of attending an engaging workshop led by some of the foremost experts in the field. The webinar sessions are designed to provide practical insights and strategies for decarbonizing our building sector, paving the way for a more sustainable future. Get ready for an immersive learning experience that will equip us with the tools and knowledge needed to drive positive change in our industry. Without further ado, let us commence today's session. Here we have our speaker for the day, Mr. Shiv Kumar Batra, Manager at Carrier Corporation. A short bio on Mr. Shiv. Mr. Shiv Kumar Batra is an electrical engineer with over 21 years of extensive experience in the electrical and HVAC industry. Currently serving as an air-cooled product management specialist at Carrier Corporation, he has a rich background that includes a 9-year tenure with the Neptune India Limited, specializing in power quality audits. Shiv played a pivotal role in representing Carrier in forums such as ISHRE and BIS during the information and revision of Indian chiller standards and the National Building Code. Notably, he co-chaired the ISHRE SDO Core Committee from 2018 to 2021. His credentials include lead at AP, Griha Elevator and Trainer, IGBC AP, GEM AP, ECBC, Master Trainer BE, and Data Center EPI AP. Shiv actively conducts HAP training programs with MEP and energy consultants, collaborating with ISHRE chapters. Additionally, he contributes to various ECBC programs, engaging with stakeholders across diverse sectors. Today, Mr. Shiv will be speaking on the topic optimizing building systems for energy efficiency. Over to you, Mr. Shiv.
Thank you very much for the introduction, and good afternoon, everyone. As the members mentioned about myself, I'm currently working in Carrier Corporation, right? So let me start with let me share my presentation to you. Yeah. So what I've done I have divided this presentation into 3 modules. So one module will be just touching base on the why we are actually talking of the HVAC and why we are talking over the building when it comes to decarbonization part. Second would be that, okay, what HVAC is all about in a building. And third part would be around the how we can optimize the existing systems. And when we have to say optimize, what was the challenges that we were having earlier and how this has been overcome with the latest technologies coming across. So this is a series which will be starting from 1st of December to 20th December, and various topics will be discussed which are related to building. And one of the topics that we will be covering up today is HVAC, and I'm representing on behalf of Carrier over here. So if I look out the global CO2 emissions, we all know about that our coal emissions in the global, we are at number 3 after China and USA in totality, right? But if you look at the per capita, we are still at the, I would say, lowest one, 1.6 metric ton per person, as compared to, let's say, if we talk about Dubai or if we talk about US, then the question comes why we are actually talking in India. We should be more talking about in Arab income, Middle East sites or in US. So let's see how actually this all translating to. So now if we talk about overall, the typical building environment generates 40%, and out of that 27 goes into the operation. That means once the building is set in operational, it is still, sorry, let me just share my complete screen. Yeah, it contributes something like 27% of the carbon emissions. Globally, actually contributes something like 15% of the emissions. So it's a huge number when it comes to the overall carbon emissions which is happening in the world. And this is the second most, topic which can be addressed if we do it correctly, which can reduce our temperature or the target that we have to reduce down the ambient temperature by 1.5 degrees C. Now, in the terms of a space cooling, if we talk about energy consumption and annual carbon emission, so we can simply see that how actually overall systems are concerned. So if we talk about energy, the residential is around 38%, and if we talk about carbon emissions, again, that's a 46%. But there are subsequent other packages also which are there in the chiller system, VRF packages, fans, air cooled. So it is not only about you focus on one part, which is residential, or you focus on the commercial, it will take care of the whole problem. We have to take it both the things because both are replicate to each other. So this is the same thing which is in different format. What has happened in 2017 to 2027 and going to be 2027, how it has improved as compared to the earlier years. Now, this is the similar slide which we have shown in the first one, but just a replica how actually it has gone from 1970 towards right now 2023. So as I mentioned, Middle East on the top, then USR is on the top, and then UK, world, and China, and we are at the bottom one. But the challenge what over here is that our population is increasing, our demand is increasing. If we will not react today, it might happen in next 5 years or 10 years time in the line. We will be ahead of what is happening in China or world or average world number or UK number. So we have to act today to make sure that we are in the lower numbers. Otherwise, we will be surpassing the world's average or the prominent USA or China numbers in terms of energy consumption. Now, another fact which is very important to understand is the price of the cost, energy cost. So currently we are at around 6 rupees on an average. If I take a national number, 6 to 7 rupees. But if you look at what happens in the Singapore is around 23 rupees. That means around 4 times. Now, what we have seen is the same increase happening up in Punjab, Kerala, Andhra Pradesh, Haryana, Karnataka over the years that the price of the electricity has gone up. Now, why this is going up? It's because of 2 reasons. One is a short of supply, and second is high in demand. So both things are happening simultaneously. One side, we are burning the fuel, so we are short of our resources. On other side, the demand is increasing. If we talk about 10 years down the line or 15 years down the line, we might not be using the air conditioning at our homes. And it is considered to be as a luxury, that is somebody is having an AC. But now this has become a necessity. Even I remember in Bombay, recently I was there, and I saw near to the airport, there was a slum area. And I saw that even the ACs are there in the slum area. So it has reached to a place where it has no longer be a price barrier. It's just a comfort that they required it, and for that they're ready to pay for the first cost. And it gives a huge impact on the grid. And the question again comes up, why we? Because there's a transportation, there's industry, and then there's a building. And as I mentioned, 40% of the energy goes into the building side, building envelope, or building environment, sorry. And out of that, 40% goes into the HVAC. That means overall around 15 to 16% of the energy that we generate globally is being consumed by the only HVAC that we use in our built environments. Now, there was a huge talk which we were discussing it about in recently that right, we have windmill, we have solar, so they can take care of it. But that's a very small part of it, because that will be happening it up only at the user end, right, which is the right way to do it. But if we reduce our demand itself, let's say by 50% or 20% or 10%, that will have 4 times impact on the resources that we will be using, because we use approximately just 24% of the energy which we generate in the station side. So if we
Mr. Shiv, please unmute yourself. We are unable to hear you.
Is it from the first slide or it is now only?
Now only. Thank you.
Okay, great. Okay. So I was just thinking about that while renewables are there, then why we should be worried about the whole process of decarbonization in the whole built environment of the building. The reason for that is unless and until we reduce our demand, what is going to happen is that we will be, for example, I tell you, let's say we have a building which has a load of 100 kilowatt. Now, if we have to make a net zero, we have to put 100 kilowatt of solar. But again, that 100 kilowatt of solar, by putting it up, it is not going to make it net zero, because then it has to generate more so that when it is not sunny, it can also feed that time. So what that means is we should actually put approximately 150 or 170 kilowatt system so that it can generate such a power which can actually feed the 24 hours in a cycle. Now, to do so, we will require a fund. That is one part of it. But let's say there is some problem in a solar. What will happen? We will again depending upon the grid, for which 1 is to 4.2 is a ratio. That means if I have a connected load of 100 kilowatt, my prime fuel burning will be around 400 kilowatts. So now if you do the improvisation on the building envelope side or the building built area envelope itself, and we reduce this demand of 100 kilowatt to let's say 50 kilowatt. So what happens? The moment we do 50 kilowatt, at the same time we have to put renewal now instead of 150, we can simply put 75. So we save on the cost. That's the first benefit to the end user. And at the same time, when we have a requirement now 50 kilowatt, instead of having 420, we can self-sufficient ourselves with a 200 kilowatt of prime fuel. So it saves energy at the sourcing, and it saves for customer at the user end if we can make sure that we reduce our demand. Okay, so I have taken the conventional building approach. So it's an office building which is there with the 6th floor and fully air conditioned, wall to window ratio which can consider 65%, and on a lighting side, 14 watt per square meter, 500 lux per square meter. It's a very conventional office building that we have. We have an HVAC chiller, COP 4.5. We put non-VFD equipment, and we have a controls zero. So there's no light control or heat recovery or economizer or VFD controls. And we find it out that this building is going to get constructed in something around 60 crores, and it will be consuming something like 348 units per square meter per year. Now, this is something which we can say as a base building, and which if we start doing ECBC or some code which can improvise overall building performance. So we picked up a code which is there with us right now, which is called energy consumption building code. And let's see how much we save. So from a conventional building, if we start adopting the strategies which has been defined or which has been laid out in the ECBC code, we can reduce our conventional demand from 348 to something like 197, which means by just improvising on the envelope, we reduce from 348 to 318, and lighting into it 343, and something like control HVAC into it, we come to 224, and the moment we bring in BMS, we come to 197, and it saves something like 37% energy. So 37% energy demand has been reduced. That meant whatever we were consuming per square meter per year from 348, we come to 197, and we only incur 63 crore. So that means only additional price of 3 crore has been put in. Now let's see what's an ROI comes in, right? So for an envelope side where we spend around 1.2 crore, we will be getting a payback something like 1.24 years. In terms of lighting, we get immediate payback because the moment we remove our existing 14 watts per square meter to something like 5 watts, right? It reduces my HVAC demand. So one way I incur more cost in putting LEDs, at the same time I can reduce my HVAC load. Similarly, HVAC component, I incur more to put VFDs or to more optimize HVAC product, and we save a payback of something like 0.2 to 0.4 in a year. BMS and controls, while it costs something like 1 CR and the payback is calculated as something like 0.4, but this BMS is not alone, right? So BMS does not actually save you upfront cost in terms of operating. So let's say if you say my BMS is on and BS is off, it will save me money, so it is not going to happen. Unless and until you have the right controls. So building management system is only just to tell you what is on, what is off. But unless and until you have automatic control system in it, the savings will not come in. So that's why I mentioned BMS, which normally people say that putting a BMS will save energy. I would say no. Unless you to have a good controls, automatic control system in it, it's not going to save energy. Why we will discuss about this in few more slides in subsequent presentation. Okay, so we all know that solution is there, energy consumption. We can simply put solar, but that will solve the purpose. But my answer is it's not going to solve the purpose immediately or in a long run, right? Reason being, solar, it is not available throughout the year, right? There will be earthquake scenarios. There will be some dust coming in, so performance getting deteriorated. So the far most better solution would be first reduce your demand. Now, before that, let's say try to understand why everybody is talking about it. So now if we have a cluster of buildings coming up together, right? And the energy demand without any building conservation will be something like 88 megawatt. I just calculate some, 50 odd buildings and we say that, okay, this is going to be the requirement. The moment we put energy conservation in a building, our demand comes to 56 million megawatt, which means now I can add more buildings into it, or there will be no extra burden on the district supply which the government has to provide. So it's a win-win situation for developer, win-win situation for the government supplies also. So now the government can invest more on infrastructure rather than building the power backup for the resources. And by the same time, if we will not increase the number of buildings and we reduce the demand, it will reduce our carbon emissions. So that's a direct link why all we are important. Let's say when it comes to building owners, building developers, the government and their emission people. So the three questions which comes into the mind of HVAC consultant is which system to be used, what should be the capacity, and the most important one is efficiency. So people say the third one is the most important. What's the best energy efficiency level of product which should be installed? I would say this is the last one. The first two are the most important. Select the right product and the right capacity. I gave you an example from a different source, right? For example, we have to go from Delhi to Bombay, right? What should we do? Which is more economical, which is more efficient? I would say take your bicycle, that's the most efficient. No petrol, nothing is going to be consumed. But is it feasible? How much time it is going to take? So we have to select what best goes in. We can go by bus, but it is going to take 2 days time. We can go by train, it will take 1 day time. We go by flight, it takes 1.5 hours. So we have to select which system has to be installed for my application and what should be the capacity of it. For example, if one person has to travel only and there is no other, right? It doesn't make to fly with the flight, right? You will not be using flight for just one person, right? We need something like 300, 400 people to travel. Similarly for train, similarly for bus. And if we have only 20 people to travel, we will not put everybody into the car. We will take either train or flight. So similarly in HVAC also, it is very important to understand which system to be installed and what should be the capacity of the system. Now, before we jump into the second question, I would say try to understand why it is important to have the exactly what's requirement for my plant room. Because if it's too small or too high, it's a problem. If I install more than what is required, what is going to happen is I will be incurring first cost. That is number one. Number two, I will be inefficient in performance because it is oversized. If it is undersized, I will not be meeting up the requirement. I will be switching on and off. So thermal imbalance will be there. So it is very important that we should have a right calculation for our energy demand. Now, to understand the building physics, there are three components and on or above it's an environment. So first is envelope, what my building is, what system, that means what kind of electrical systems or HVAC system goes into it. Another one is occupancy. So how many people are going to be there? For example, I am not sure whether I have this slide with me or not, but I can give an example. Let's say when we decide for an hospital or an hotel, it always has been seen whenever it opens, it's very comfortable. People love to go there in terms of comfort, right? It's a hotel or a hospital, everybody is very happy, even in offices. But over the period of time, we say that the system is not very, effective. So system is there, but what happens is the occupancy goes up. And when we design, we never anticipated that kind of an occupancy. For example, the government hospitals, right? So what happens in the government hospitals? New government hospital, less people comes, everything is good. But the moment it gets old, it gets named, people just jump into it. So or a hall which can accommodate approximately 100 patients, it is accommodating 500 people. So when they have to accommodate 500 people, definitely they can't, give the comfort which they were getting it when they were 100. So occupancy is important. And over and above is the environment. Now we have done some work on the environment side. So before just to give you the Indian climatic zone distribution. So we have hot, which is from Rajasthan and Gujarat side. We have warm and humid, which is our coastal region. We have composite, which is our central part. We have moderate, something around Bangalore, which is very moderate. We doesn't require any air conditioning 5 years back, but now they also required air conditioning. And we have cold, which is on the top, not which is our Himalayas or the Jammu Kashmir, Ladakh or Himachal side. Now, this is one typical office building which we created in our tool, and we use the different cities to see how they actually perform. So if you look at Delhi, so Delhi, the temperature goes as high as 45, right? And the maximum temperature or the building requirement comes up in monsoon, which goes to something like plus 1000 ton. And it goes as low as something like 0 degree or 5 degree temperature, right? Which is now December. But still air conditioning is required. And if you go to any hospital or hotel or office, right, we see that air conditioning is on. So there's a huge load variation. In fact, there's a huge ambient variation also. The same building, if I move from here to Trivandrum, so what happens? My environment window is only 35 to 22. And you will see everything is between 1000 ton to 250 ton. So what has happened? Same building, everything same, your demand and your variability is vary. The same building, if I bring it to Bangalore, so what happens? My tonnage requirement, which was around 1100 in case of Delhi or 1000 in case of Trivandrum, comes down to 800 kilowatt, 800 tons, sorry. So what happens? Because the maximum ambient is low as compared to what is happening in Delhi. So that means a building which is coming up in Delhi, the building which is coming up in Bangalore cannot be same in terms of an HVAC design. They have to be different because their requirements will be different. So normally what happens earlier, what I've seen it up number of times that we do a copy paste kind of an arrangement. It's a hotel which is coming up in Delhi and coming up in Bangalore. So people simply put the same amount of capacity of chiller, same amount of air system. That's not going to work it out. So we have to design the building as per the environment required. That is one. Second thing, most of the green buildings are coming up in Bangalore. The reason is the climate conditions are good. So we should actually build up our build environment where we are close to the environment, but we can't build everything in Bangalore. We have to be in Delhi also, Chennai also, and other places also. But important point is that the HVAC system should be responsive towards the environmental demand. Now there's another thing which is called adaptive thermal comfort. So normally what happens, we keep the temperature something like 28, 27 to something like 22. I met number of people who say that the temperature that they maintain in their offices or at home is something around 20 to 24. Why it is so? Because they feel comfortable. Is it for everyone? The answer is no. So there is an adaptive thermal comfort calculation which is given in the National Building Code. A research was done and table was created. They specified basis the ambient temperature, you should actually set your indoor temperature. So if the ambient temperature is something like 45 or 50, it will be comfortable at 27. But if your temperature is around 35, you will be comfortable at 26. And if your temperature is around 25, you will be comfortable at 25. So you don't need air conditioning. So if you are at temperature 10, that means outside temperature is low, you need 25. So 25 is something that's a moderate temperature. We should be maintaining it up. But if the outside temperature is high, you can increase 1 or 2 degree temperature. And that's where the controls comes into the picture. Basis the ambient temperature, they can adjust the internal temperature irrespective of what you have set as a manual. So there will be a, I can say, a manual changeover or manual carryover, which can actually change the set point from the set point which we have decided when we start the air conditioning system. Now the question comes, okay, that's good that we know that, okay, there should be some system and we have to follow it, but what are the systems, right? So let's understand the system. So there are two types of system, and before that, people ask me what's a ton of refrigeration. So it's a 1 ton of refrigeration, the cooling power needed to freeze 1 ton of ice, right, at 0 degree water to ice, so at the same temperature for 1 day. That becomes your 1 ton of refrigeration. And people, we can convert it into BTU per hour, which is around 12,000 units, and in kilowatt mechanical, which is 3.517. Any refrigeration system will be a component something like this, right? So it will be absorbing some energy, and we will be doing some work, and we will be throwing out the energy. So this is normally what we do in our household also when we clean our house. We don't clean our house by just saying that we are cleaning it up. We remove the dust and house becomes clean. Similarly, if we want to cool this room, we can remove the heat. So heat is absorbed, and we do some work by either vacuum or some mechanically or physically we clean that, and the heat gets out. So that similar thing happens in the refrigeration also. And these are the 4 components. One is the heat rejection section, which is on the top, and then we have a vapor pump, which is a compressor, and there's another coil which is required heat absorbing, and then the pressure regulatory. So these are the 4 components you will find out in any of the AC, whether it's a window AC, split AC, or car AC, or refrigerator, anything, this will have all these 4 things. And to give you an example, which is a very homely one, so let's say you open the fridge, so you find it cool. So somebody is absorbing the energy from that inside the fridge. And if you go at the back of it, you will find there is a one compressor, there is a one small pressure valve, right? But we never find heat rejection section, right? Nowadays, because that's embedded in the body itself. But you will see that the body itself from the rear side is heated. So it is injecting the heat from the back side of the fridge. Now there are two types of systems. Let's say if we come back to the refrigeration only. So one is called direct refrigeration, and another is called indirect refrigeration. So when it calls direct refrigeration, that means heat is removed by the refrigerant directly. And when it is called indirect, that means first it will be absorbed by water or some other medium, and then it will be transferred to the refrigerant. So this is a typical example of a direct refrigeration system where we have one compressor, we have a condenser, and we have a coil where you are using a refrigerant in the coil, and air is transferring its energy with the coil only, right? So what is happening? Air is transferring its energy to the coil. Coil is getting into the having a cold refrigerant. So ultimately, you are cooling the air, and cooling air is going by a supply duct. Heat is absorbed, and then it goes back to the return duct, and the return fan. Some part will be exhausted, some will be absorbed back into the system to make sure that it is economized rather than simply bringing the fresh air from outside. These are the few residential products. We have windows, we have splits. So these are the one which we normally see in our households. Then there is another very popular concept nowadays, which is called VRF. So what is the difference between VRF and window split ACs? I would say it's only one. Indoor, there is no difference. There is some indoor unit and there's a refrigerant pipe. Same thing for 1-to-1 or 1-to-4. Now, only difference is outdoor installation. So in case of a normal split ACs, we will have, let's say, a house which is having 4 rooms. We have 4 indoors, we have 4 outdoors, and we have to maintain all 4, right? Now, instead of having 4 outside, we can install 1, and then we can optimize the capacity of it. For example, I have all 4 rooms and all are of the same capacity, 1 ton, right? And there are 3 people in a house, so definitely they can't occupy 4, right? Around 2 rooms will be occupied. That means remaining 2 will not be occupied. In worst condition, 3 will be occupied. Now, in case I go with a window and split model, I have to install 4 units. But in case of VRF system, I can install 1 outdoor and 4 indoors, but a lower capacity of the outdoor capacity. Instead of 4 into 1 ton, in case of window split, I will install 1 of something like 3 ton. That will be sufficient. So I'm reducing my 25% of the connected demand. This is typically can be increased when we have an office building where we can, instead of installing 1 dedicated room or dedicated units across the rooms, right? We can have a VRF system at the terrace and we can lay down the piping and we can connect them up. And this is something in outdoor, which is of a different capacity, and we have a wide range of indoor unit applications. So we can have cassette, we can have fan coil units, we can have splint pack. So n number of options are there when it comes to connecting the indoors. And the application for the VRF is condominium, residences, farmhouses, small offices. So this is a typical installation which we have seen it up. Sometimes people come and say that why not do in large offices, because then you have to make different circuits. It is possible. I'm not saying it is not possible. It is very much possible. But again, we have to see how we can optimize the outdoor installation sizes. So if we have, let's say, 1,000 ton of requirement, definitely with VRF also that is possible. But what is going to happen? Let's say if my one circuit is of 50 ton, then I have to install approximately 20 circuits and 20 similar kind of installations. So what is going to happen? My terrace will be full of outdoor units, right? So instead of that, why not to put chillers? So that's the reason we say that small offices, it's good when you have a requirement of something like 50 ton to 100 ton or 150 ton, let's say 200 ton. But beyond that, if the requirement goes off, we should actually try to start focusing on the chill system. Another option is sometimes we have to install even to the large offices. It is coming in a staggered way. For example, there are tenants coming in, right? They want independent controls, independent system. They don't know when they will be coming it up. So it is being advised, or the consultant and architect design or the customer request that let's have an independent VRF systems also. So that also is possible. I'm not saying that it should not be done. Depending upon the requirement, that should be selected. Another solution is indirect refrigeration, where your refrigerant circuit transfers energy to water, and then water transfers the energy to the air. So in the same remaining low side is same, that you will be supplying the cool air inside the room, absorbing the heat, going back return duct, exhausting 20% of it, bringing it 80% back in use, bring 20% fresh air, and then again transfer the energy to the system. So this is also one of the way of economizing or improving the efficiency of your system, that you use the fresh air as and what required. For example, if there's one person sitting in it, or there is no person sitting in it, right? Then we need minimum outdoor air so that it should not smell. So if I can give a reference of hotel rooms. So when sometimes you open the hotel rooms, you find out there is a carpet smell coming up because there was no fresh air inside the room and room was locked, right? And sometimes when you visit the hotels and you open the door, it's very good in terms of fresh air. That means they are using fresh air when the room was not occupied. They have to use minimum, right? So around 1% or 2% of fresh air, that would be good enough, and they can circulate and they can remove the fresh smell from it. Now, let's say there's a room which can accommodate, let's say, 100 people, and they require X amount of fresh air. Now, if the people are not 100, the people are only 10, do you still need X amount of, or let's say, X amount of fresh air? The answer is no. We can reduce this X by 10, right? Because the people are only 10% of it. The reason being, the more you bring outdoor air, and if the outdoor air temperature is high, that means you have to cool that air to be comfortable. So use the fresh air as what is required inside the room rather than just, filling it up with the fresh air. Now, there are two types of indirect refrigeration. One is called air cooled, another is called water cooled. Let's see what's the difference in it. So when it comes to air cooled, so you put your chillers on the terrace and you have the low side, which means your piping will be there, your AHUs will be there, and there will be some storage tank or the makeup tank that we install it up depending upon what kind of installation it is. But the more important is you have an air cooled where you are rejecting the heat outside the building, what you captured from the building via air itself. So the refrigeration is transferring energy directly to the air. That is called air cooled system. Now another system which is called water cooled. So what happens? You put the chiller in the basement, right? And you put your cooling tower on the terrace. So remaining everything is same. You capture the heat from the building, from AHUs and then to the pipes, and then it goes to the chiller. But now chiller has to reject energy out of this building. So in the earlier one, we were rejecting energy directly to the air from chiller. But in this case, we will be first transferring it to the cooling tower, and then cooling tower will coming in contact with the air and it is rejecting energy out of the building. So that is called water cooled system. Now, when this is happening, evaporation or some energy transfer is happening in an open loop in cooling tower, there will be some losses of the water which will happen. To make up those losses of water, we need a makeup tank. That means we should have some tank storage for water. And how we'll get the water in the makeup tank, because we can't use potable water in the cooling tower. So for that, we use STP. Now, STP is possible when it comes to hotel, when it comes to hospital or an office building. But what happens to the data center application? So for data center, we can't put STP. So normally you will see the data center people use air cooled system because they can't arrange for the makeup water. And wherever we have a scarcity of water, we should go with the air cooled systems. For example, in Rajasthan belt, where we have a scarcity of water, definitely we don't want to use even the makeup water, which is from STP, in a cooling tower. We want to put it in a field so that we can use it for greenery. So it has to make a balance with the regulatory requirements, which system to be installed, what you can make it out. For example, if you're coming up with a big hotel, definitely there will be an STP and you can use that water for cooling tower. But if it's not a hotel, it's a office building which will be operating only in a day hours or in the evenings, then you have to look for air cooled systems. These are the typical air cooled and water cooled pictorial views, and this will be same. It's not respect to the carrier, but it is to be any brand we see similar kind of air cooled and water cooled pictures will be there. And the typical applications are malls, data center, airports, and commercial complexes. Now, one of the inventions which has been done in past 15 years, I would say, is the putting a VFD on the chillers. Right. So I still remember when I joined Carrier in 2006, we were struggling to convince people to put VFDs on the chillers. So they prefer to have a constant speed, and that's what they used to do. But when we get in touch with them and we do the simulation part, when we calculate the annual energy performances, we find out there's a huge difference when you put VFDs on the chiller. So now this is a typical chiller application. So let's say we have a building which is a 100% load chiller. So on mechanical, on 100%, both are consuming same power. But the moment it runs on a part load, your VFD chiller is more energy efficient as compared to mechanical. But the question comes, why should we run a chiller on a part load? We should always be running on full load. But that doesn't happen actually. And I will give you the details, not here, not here. This one. Yeah. So that's a part load. So any building which we design, it is actually designed for full load for a design day weather when it is fully occupied. So full solar load is there, full equipment and lightning load is there, full ventilation rate, and all this happens simultaneously. Now you tell me any scenario, this is not going to happen, let's say more than 1 or 2%. Or let's say the recent study that have been done by the first specifically for India is around 6%, right? And most of the time it will be running on a part load. That means around 94% or let's say 90% to be on a safer side. My chillers or my building will be operating on a part load when it comes to HVAC load on the building is concerned. Now that means 90% of the time I have an opportunity to save energy. And how? Just by putting a VFD on my component. So which components can actually be used for, or how actually I can use for VFD is this one. Putting a VFD on my motor, right? It saves energy. So if you reduce the RPM by 10%, it saves 27% of energy. And if you can reduce it by 50%, your energy savings are something like 88%, which I still say that, okay, this is not going to happen, but something like 100 to 90 or 75% RPM reduction is possible. And if it happens, there is a very high opportunity that you will be saving around 50% energy onto the motor consumption. Now, this typically happens for a building which has a total building load of, let's say, equivalent to 2 chillers. Definitely, I will not be putting 1 chiller for the complete building, because if it has some challenge, then my 100% building is down from the HV support. So I will be putting 2 chillers. Now what happens when your 1 chiller is running, right, and it goes to the 100% load? So on vertical axis, I have a chiller loading. So my chiller load is 100%, but the building load is 50% because I'm having 2 chillers. And then the moment it crosses 50% of the building load, my second chiller comes into the picture, and the both start running towards 100% the load. So the moment it reaches to the 100%, the building load, my both the chillers are running on 100%. So now let's see what happens to the performance of my chiller. So the same thing on my horizontal line, it's a building load, and on vertical, it's an IKW per ton. So if I look at my performance when it's 100% building load, 100% both chillers are running, both are consuming same amount of energy. But when they are running on 50% building load, right, both the chillers are running on 100%, but their power consumptions are different. And that's an opportunity area. That means the moment we come down lower on loads and we run down number of chillers in a part load conditions, we will be saving energy. And this is something which is, again, we have taken it from the initial slides, where we try to show that the buildings actually runs on a part load. So each dot is an TR requirement. So the building load requirement. For example, if I talk about Delhi, so every 1 hour has been plotted into the graph. That means there are 8760 hours of operation, which we are seeing it up. So for Delhi, Ahmedabad, Calcutta, Nagpur, I would say these are the places where we should actually go with the VFD for sure, without any doubt, right? Even in Chennai also. We can think of Bangalore, Goa, or Trivandrum, but Bombay, again, we have a large amount of areas when we actually having a varying load. And these are some air side products, which are AHUs when we have a large amount of volume to be thrown inside the room, right? Which is a big halls, or we have a distributed the airs inside the rooms, or we can have a fan coil unit, the one which we normally use in rooms, right? In hotels or in hospitals. Another aspect is pump cooling tower. So while we discussed about water cooled system where we are rejecting the energy into the atmosphere via cooling tower. So these are the cooling towers which we normally see in the power station, so not in our normal buildings. So in normal building, we have this kind of cooling towers which are either induced or cross flow and counter flow. So we have to select which one is better in terms of a requirement. So cross flow will have low pressure drop, it will take more energy. Counter flow will take low approach, but will consume more power. So we have to make a combination which suits best for my application. Then coming to the cooling tower, we have another important aspect to understand that while we put the cooling tower, but what's the life of the cooling tower and how we define the cooling tower. So cooling tower is nothing but a big tank of water which we are sprinkling it up and transferring the energy into the air. Now, if the water is not a good quality of water, what will happen? Let's say if I have more salt, salt will get passed away. And what will happen? That salt will go to your chiller and your chiller will fail, or it will start consuming more power because it has to transfer now energy first to salt and salt to water. So we have to make sure that the water that we are using it's of a good quality. So these are the few terms which I mentioned. Then there's the algae formation. So if we put our cooling tower where we have a direct sunlight coming up, we got an algae formation, and that's a bad conductor of energy. So what happens when we have this algae formation? You will find your soap water is feel something like soapy. And when this happens, your heat transfer is reduced, and because of that, the efficiency of your complete system is get deteriorated. So always make sure that you don't have an algae formation on cooling tower, and at the same time, the water quality is being maintained. Another thing which comes up is the pump. We have talked about in indirect pump, indirect DX system, we need pumps at two places. One is from chiller to AHUs, and then from chiller to cooling tower. So there are two pumps that we normally use. So conventionally, on a primary chilled water side, we use one pump and we create bypass arrangement across the AHUs. This was the traditionally that we used to do, I think, 10 or 15 years back, right? Then comes a new system which is called primary secondary, right? So we use a small primary and a big secondary, and we remove the bypass line from the AHUs. Then we come one step ahead and we said, why we put two pumps? Why not to put one pump itself and take care of everything? That is also possible, and it was done. And when we see the comparison in terms of how much energy we save, so from a constant primary to primary secondary, we save something like 48%. And when we move from 48 to primary secondary to variable primary only, we save 24% additional saving. Now, that's it. So I would say no, there are few other benefits on it. And then now a latest one which is coming up is a distributed pumping. So what happens in the distributed pumping is that you had a chiller, you had a pump. Instead of putting a big primary pump, you put a small primary pump, right? And then wherever you have the AHUs, which needs water, you put pump over there to pull the water and make sure that it crosses the coil. Now, while doing so, it saves energy something like 33% from my existing primary secondary system. That is one part. Another part is it makes my system more adaptive towards the changes that I need. So if there's a small variation in my load, immediately my pump reduces the speed of my water and it saves energy. It makes my system more balanced. Normally, till now, we all used to talk about chiller IKW. I remember in number of places, we always talk of COP of the chiller. It should be high as high as possible. Why not people go for 5.6? Then people come with 6, 6.2, 6.5, 6.7. I always say that don't look it for only for the chiller. Always look for chiller, pump, and cooling tower all together, right? Our objective should be what goes in, what comes out. It should be the lowest. So input energy versus output capacity. So my input should be low and output should be high. IKW per ton should be only monitored. Now, how to start the design process? So it's very simple that you take the heat load calculation for your building. You select the indoors, you create the design, the circuit indoor versus outdoor, and you select the outdoor selections and you finalize that design. Now, the most important part is people say that it's a heat load calculation. I say no. Heat load calculation is just garbage in, garbage out. The most important is the data input from the customer. And in this case, my customer does not mean only the end user, but the architect who is actually designing the building, right? So the input coming from customer architect is the most important thing. If we get the right inputs, we will be designing it absolutely correct heat loads. But if we get the inputs not correct or it's a vague, people will be 5, people will be 10, but there's a 50% load variation, right? So we take, as a consultant, I will take 11, right? Because I don't want to get failed. So it is very important that we put the right inputs from the customer. We are putting glasses on the wall, right? It's a single glass or a double glass. Initially, we all say, okay, it's a double glass. But when it goes to the negotiation, we say, okay, double glass is expensive, let's put single glass. But what happens? The moment you change the glass, the heat inside the building comes more. And when it happens, it increases my demand. So sometimes it happens that everything was done right, but finally we find it out, oh, chiller is not sufficient. It's underloaded, right? The load is more and the capacity is smaller. But we say that this has been based on the input that we got it from you. There's a change in the site side, there will be variation. So the input from the customer is the most important. Heat load calculation, I would say it's an Excel sheet. Anybody can do. We should follow that one. But the input is something that we have to see what is actually being used on site. That should be considered as an input. Now, there's an ECBC code which talks about there are a few things which are mandatory, then prescriptive approach, alternate method approach, low energy cost, whole building. The intent of whole this is make sure that you follow them up and you reduce your demand and buy the best product out of it. Right. So on a mandatory side, there are some mandatory which are being given for the chiller COP numbers when it comes to split ACs, right, or a domestic appliance or domestic air condition, they give a star rating to it. And boilers, the efficiency, VRF, again, they give some numbers, right? So we just simply follow that number because a lot of study has been done on this part that what should be the optimized number, which is available at a cost. It should not happen that we started putting 6.9 COP chiller, which is costing me double the cost, right? So these numbers which are mandatory, they are being considered as a more economically suitable and achievable numbers in terms of the product efficiency. Now, another thing which I want to bring it up here is the star rating. The people always call, buy a 5-star rated, 4-star rated, or 3-star rated product. I say 5-star, 3-star rated only tells you about the energy pattern. It does not talk about the quality of the product. So for a meaning of quality, even the BEI label specifies that it only talks about the energy consumed by the unit to deliver that amount of output. It does not talk about the quality standard. So when you buy a product, please take care of that, which brand you are buying it up, what's the quality feedback from the industry or they show it, what kind of service network they have. For example, I have an OD, but I don't have a service person who can come and repair it up for, let's say, 15 days. And what's the point of it? Why Maruti gained the popularity? Why Hyundai get the popularity? Why Tata getting the popularity? Because they have a good service network and a good quality. And they have a good performance. So all three ticks has to be there. It's not only 5-star. So I'm not a very high influencer of buying a 5-star. I would say buy 4-star, buy 3-star, get a good quality product and use it properly. Instead of running at 18 degree or 20 degree, your indoor in your room, you maintain 27 degree. It will be more efficient than 5-star, right? So instead of buying a 5-star, buy 3 or 4-star, use it optimally. It will be more economical. If you have money, you want to spend 5-star, go for a 5-star, spend more money. But again, operate it at 27, 29. It will save you more. So is the decision ends here that you have a good cooling tower, you have a pump, you have piping, you have air duct? I would say no. The most important thing is the installation part. So when it comes to installation, these kinds of installation, what we see in the market, right? So when it was first installed, it seems good. But when you start putting more and more, all heat is ejected at the one place, which is not good. The second installation looks very good in picture. But if you look at carefully, what is happening? The heat from one unit has been thrown into the other one. It's not a good installation. Third one, what is it? We are rejecting the heat under the carpet, which is again, it is not getting involvement to the environment. So after some time, that area will get heated up and it will not able to reject the heat. The insulation of the pipe is gone torn on. This is a normal typical problem in residential circuits which we see. We always clean our indoor, we always clean our outdoor, but we never see the piping insulation. If there is an insulation problem, it will reduce down your capacity and increase your electricity bill. Now, this is another example which I've seen it up in Kerala, right, where they were using the condensate water. Instead of throwing it on the road, they put it up into a flower pot, right? So this is the best example, I would say. Another thing which has been a big initiative from Bureau of Energy Efficiency of using a fan with air condition, right? So normally people say that when I'm switching on the AC, why should I need a fan? But I would say if you use fan, it will give you a same comfort at 2 to 3 degree higher temperature. For example, whatever comfort you are with 25, you switch on your fan and you will see that you can get the same amount of comfort even with 27. But it costs me the energy when I switch on the fan. The energy consumed by fan is in watts, something like 3 watt or 10 or 15 watts or 25 watts, right? But the saving which we will get of 1 degree increase in the temperature is 3% of your total AC. So if you increase by 2%, you are saving 6% on your AC bill, and the power which goes into the ceiling fan is negligible. So always use ceiling fan along with the air conditioning. Now coming to the BMS part, right, which I mentioned about it. So the new terminology which people used to talk about is IBMS, right? So this is the Integrated Building Management System. So there are 4 systems which are there. So one is called Chiller Plant Manager, which we normally do. Let's say you have a chiller, you have a pumps, you have a cooling tower, you put VAVs, we put VFDs, and we try to bring it into one, separate desktop or a computer, and we say this is my chiller plant manager. It is only controlling the chiller plant manager. Then as for the next level of offering, which is called connect services, right? So which is you can connect all these equipments to IoT. So it remotely also you can see what is happening. You can see how these systems are going to respond to you. So this is something which is now very much globally acknowledged or accepted, right? Which is called life cycle thermal optimization. You can actually see if my temperature inside the rooms are increasing, right? While it will take their own time to, increase the load on chiller, immediately it can increase the load on chiller. So that will give you a better thermal comfort and a better response. Then you can actually do something like data collection and contest. So you capture the data and you store it up in your machines, and then make sure that on particular day with particular people, you will require this much amount of air conditioning. So instead of responding sometime, normally what happens, you need 4 or 5 inputs. So one input is definitely what is inbuilt in the system, which is temperature coming from the return water temperature. But sometimes that the temperature sensor is not working. So you will not get comfortable, right? Because it is not sensing the temperature. Similarly, there can be another source of information which comes into it, which is occupancy. So if my occupancy is going up, definitely the temperature will go up. So instead of depending on one set of information, you can take 3, 4 systems, you can take their inputs, you can simulate it up, and you can adjust your controls. That will bring the savings. So these are the few projects which have been done globally, right? So I will not get into it. Another thing is called BMS architecture, which actually means that you will have all the electrical panels, you have control, so you can switch on, switch off, you can see what is happening, how much power it is consuming, right? Then you have life saving, which is your firefighting and all those things. Again, you require another desktop version. And then you have a security where you have cameras. Now, I always say that when you put for IBMS, all this comes on a same platform. Instead of creating 4 platforms, you can have one platform which shares information from A to B, B to C, and C to A. For example, if there is a power failure, right, immediately it can switch off all the essential requirements and it can come out of it. There is a fire, the camera will start recording, right? If there no more number of people have been observed by the camera person or the camera team, right, it gives an input to the chiller side. So they all talk to each other. So this was there on the building side. Now there are two case studies which I want to present it up, right, before we come to the last one, which is, so one is, let's say when we talk of what to select in terms of, when we go for optimizing a building. So high usage variability and design and low usage variability and design. So if you take the large usage, right, it's cooling tower, your pumps and your chillers. Low side, what is the low side is your vertical thermostats, others are airspace and very few light parts. So these are the very small power consuming equipment. So we have to focus something on the chiller side or the pump or a cooling tower side, which consume around 45% of the total energy. So what are the typical potential that we have? For example, if you look at the chillers, so if you put VFDs on chillers, if you make sure that your chillers are ECBC plus or super ECBC, you go for a ceramic or magnetic bearings. So there's a potential that it will save something like 10 to 45%. This is the conventional chillers or the standard chillers that we normally go for. Air side, you can replace the DIW fan with EC fans, VFDs on AHUs, two-way modulating walls. There's a potential of around 15 to 20% saving. On cooling tower, CTI approved. I think that's normally people do, but still sometimes to save on cost or sometimes to select some particular brand, you might not get, but you should always insist for it. It assures that whatever product you are buying, it's not underrated, right? Fan stage control based on the temperature or replace the fans with the EC fan. So that also saves something like 20 to 20%. While there could be saving potential if you consider different material for the cooling towers, that also saves energy. Then comes pumps. So differential pressure sensors, VFDs on pumps. Normally we do, but there are next stage of pumps which are coming up, which is a distributed pump, which can save another 10 to 20%. So these are the typical, I would say, areas where we can save energy on the HVAC side. So there are two case studies, which one is of a Taj Palace Hotel in Delhi, right, where one 500-ton tri-rotor water-cooled chiller is placed, 300-ton, and associated pump cooling tower was replaced with VFD drives. overcome the critical challenge of space constraint of cooling tower on the rooftop. So that was also overcome. Developed a chiller plant system for water cooled associated pumps and cooling tower low side AHUs to improve overall efficiency, integration lift, also done with the PSM. So they put a strategy that they will not be responding based on the return water temperature alone. So as the load changes inside the building, and they take the inputs and they immediately change the operation point of the chiller. Existing 3 into 300 TN chillers was along with pump were retained as backup and was taken care of the increasing load demand. An automatic tube cleaning system was installed. So automatic tube cleaning system is what that it is. Normally in the cooling tower, what happens? My salt get deposited in my chiller condenser. So what happens once the salt get deposited? It is very difficult to transfer energy to water at the same level when it was new, because it becomes a resistance in between the heat transfer. So now we introduce, there are many technologies which are there which can be used, right? One of them is tube cleaning, automatic tube cleaning. So they send the very small sponge balls inside the tubes and it cleans the tubes from inside, which actually improve the efficiency of my heat transfer. So overall, when we did this, so there were some expenses which happened, right? So investment was around $350K, right? And if I talk about 350K is something like 1 CR, right? They get the payback in 3 years time, right? The plant efficiency, which was 1.1 IKW per ton, it moves to 0.69 IKW per ton. So now if I look at a 1.1 to let's say 7, so we save 0.4 IKW per ton. That means approximately 60% energy was saved, right? So energy saving was 10 megawatt units per year. This is the overall saving that they were able to achieve. Now another example, which is, and this is a customer testimonial at the BE website. So this is available even over there also, right? Another one is on the DLF side. So they have two 180 TR water cooled chiller, SOD pumps and cooling towers, all equipped with a variable frequency, overcome the critical challenge of space that's typically there. Develop a chiller plant manager control strategy. Existing water cooled system was retained as a backup for smooth operation. So energy saving in electricity bill was around 50%, right? And they also put something like $200K. They get a payback in 3.2 years time, and the 0.4 megawatt per hour was saved, right? So plant efficiency, which was 1.46, it comes to 0.73 IKW per ton. You might be saying it, why not we get 0.69? Because this is an office building, it's not a hotel building. So I can assume it up that operations are more in a day, while in Taj it would be have a different, because the operations will be in a night. So it all depends upon what kind of an application you are, what kind of saving potential. But if you look it up on 1.46 to 0.73, we saved something like 50% on the energy. So now I will open it up for Q&A, and if we have time, we can even actually, I can show you one more slide, which is on the tube cleaning system side. So before we jump into it, what kind of a cleaning systems we have, right? So I will show you this slide, I think. This is good. So yeah, so there's an automatic brush cleaning system, which is very high on cost, continuous tube cleaning at an interval of 20 minutes. Efficiency and pressure drop increases, life of the brush, additional piping alteration is required because pumps have to move from left to right and then right to left. So every time this change happens, there will be a modification which is required on the pumping side. So we put a two-way big diverting wall inside the main lines. Then automatic ball cleaning system, which is also on high cost, continuously cleaning the tubes, right? Efficiency, pressure drop, increased life of the boil is a concern, but installation is little complex when we say, because there are too many things we install it up. Additional pipe alteration is required, but this is one. Online cleaning, it's a very high cost, non-negative impact on the chiller. Continuous cleaning, low water blowdown, very high cost and limited capacity. Water softener, which is very low on cost, which we normally do, reduce the TDS. High water and chemical demand, that's something which we have to incur. RO, again, the cost is very high. Advantage is it reduces the it improves the efficiency, reduces the hardness, right? Continuous water wastage and difficult to handle. Ultrafiltration, very high on cost, remove bacteria, colored material, organic, inorganic polymer. Normally, you will see this kind of ultrafiltrations in hospitals, right? Where they have to be very particular about that there should not be any bacteria formation. Cost of handling, controls, operation, high space. So these are the challenges. Then there's another technology which is called HydroPath, which is medium on cost, compact, easy to install cleaning system. but it does not give you 100% results because it's partially clean. You need additional filter to remove the impurities from the system. So now if I come back to the one which I personally believe that this is the best one, is automatic loop cleaning system, right? So I can share you a few more slides on this. We have, yeah. So yeah, something like this kind of a system it is. So you have, yeah, so you have one heat exchanger in which the balls are actually going in, and then you collect the ball in a ball trapper. Then it comes here. You have a one injector, and then you recirculate that ball in back to the input of the heat exchanger. So this goes on continuously, right? And when the sponge is actually going through the tube, it is actually removing the dirt which is actually getting attracted in the tube. So this way it cleans the tubes, and there is no scale formation which happens on the cooling tower. Now on the on the heat exchanger, right? While in case of brush, what I was mentioning about is that you have to keep a big this diverting wall. So every time after every 20 minutes, you have to change the flow. So for example, if one side the brushes are on this side, you make this flow to go this way, and then you change it, it comes back. So this is something that you have to install it up. This is online cleaning, which is you put a centrifugal pump right between the, and you take some amount of polluted water or mineral water from the cooling tower. You scale it up, centrifugal function, all the impurities get deposited on the corner, and then you again back to the water. This is a very good technology, but only challenge is that it's a very limited size and very very expensive. Right? Cleaning, I think we all know. So, and this is the hydro part. So normally what happens, we put this kind of a magnetic field we created. So whatever the impurities we have in the water, they all get, they don't get settled down, and they charge them, right? So that when it comes back to the cooling tower, they get all settled down in the bottom, and we can remove it from the cooling tower. Right. So this was there. So now I will open it up for the Q&A. So if anybody have any questions, please feel free to. Yep.
Yes, thank you, Mr. Shiv, for the very insightful session on optimizing building systems for energy efficiency. We are now opening the floor for questions and answers to the esteemed participants. If you have any queries, please raise your hand in Teams and I will acknowledge you by name. Yes, Mr. Ramwat, please go ahead.
Telling
We
us
are on.
about of appliances
Yeah.
being used, and you said that it's better to go for a lower rating appliance instead of going for a higher one. So I just wanted to know that I just bought a air conditioner, split AC, and earlier I was using a 3-star rating. Now I have shifted to 5-star rating, and I have got energy bills being reduced by almost 50%. So
Perfect.
just wanted to understand
So,
what
so
kind-
only thing that I was saying it up, that when you are buying a 3-star AC, right, instead of what temperature you were operating it up earlier versus now. For example, if you're running your 3-star
to
AC,
temperature earlier also, now also.
correct. So now also and earlier also, you are maintaining the same temperature. So what I mentioned over there during that time is, if you are using a 3-star, 4-star AC, right, instead of buying a 5-star AC to reduce the energy demand, no doubt in it, it's a good alternative. If you have money, you can do that one, right? But I have a 3-star AC. I want to reduce my demand, right? How can I do it? I can increase my temperature by 2 degrees and switch on my fan. It will give me the same comfort, but at a lower cost. So it's all how you want to manage it out, right? If you have money to go for a 5-star, 7-star, please go. But if you want to see how you can optimize it further, let's say in a 5-star also, you have a 5-star AC. Now you switch on your fan along with it. At 2, right?
The fan I was switching on, and the temperature was 26 to 28 degree, and everything I was doing earlier also with 3-star one. But with a 5-star one, I'm getting 50% on 3,000-4,000 rupees saving, and I paid 20,000 extra for that one. So I have a pay.
Definitely, that's yes. So if you have 20,000 rupees, go for 5-star, right? If you want to get more savings on your existing 3-star, you can switch on the fan you will get that one, right? So I was comparing your fan to AC to AC. Your 3-star versus 5-star, there will be extra cost to it. And if you want to save energy, you can switch on your fan, you will save energy, right? Or you can move to 5-star. And in 5-star also, if you switch on your fan, you will further save it. So you are actually on a base above your AC with fan, AC with fan. So that delta will always be there. You go for higher efficiency, you will save. No doubt in it.
Yes, yes.
Yeah.
Okay, thank you.
Thank you, Mr. Ramat. We have Dr. Niyati here with a query. Niyati, please go ahead.
Thank you, Tinu, and thank you, Mr. Shiv, for a wonderful and insightful presentation. I learned a lot from the presentation, not just with respect to giving a brief overview how architects perceive, but also giving a very how do you decode a ECBC code? Like what does it actually mean for HVAC systems? So it was definitely a wonderful learning experience. I would also like to know about you talked about hotels per se regarding the fresh air quality and how HVAC systems. Can you also give an example from hospital infrastructure, which is where HVAC plays a huge role? Like in other infrastructure systems, including institutional hotels, you can still adopt certain passive measures, right? But in
Right.
hospitals in particular, HVAC plays a huge role with respect to reducing hospital acquired infections or improving the indoor air quality. So just an example of how energy efficient system can be built, or what are the basic few
Okay.
things that we can consider. Yeah.
Sure. So normally whenever we talk about hospital, there are 2-3 things which comes into the mind. First thing is we have to put HEPA filters, right? For sure, because we have to differentiate between outdoor and indoor, right? We have to be more filtered air inside the patient area, so it has to be HEPA filter. That's for sure, right? Second thing is we have an OT. So normally when we have an OT, we have to maintain an RH, and to maintain an RH, what we have to do, we have to make sure that we will reduce the temperature of the chilled water temperature, right? So instead of delivering at 7, we normally deliver at 5, something like 4.5 or 5 degrees, right? Sometime even lower. But what we do when we are designing for an hospital, we design the whole hospital at a lower temperature, which is around sometimes 5 or 5.5 degrees C, right? Instead of 7 degree for chiller, right? So what happens, I would suggest for those kind of an application where we have OT load and where we have a normal comfort load for the patients, right? We should actually bifurcate these two circuits. So one is only for OT, right? We can go for an industrial kind of application or a chiller, which can actually generate lower temperatures with brine or something like that. And for the comfort, we can still continue with 7 or 7.5. There are 2 reasons for it. One is this load percentage is always very variable. For example, your OT load will be around 30 to 35%, and your comfort load be 60 to 65%. We should not penalize 60 to 65% load also to operate at a lower chill water temperature. At the end, the comfort will be same. You will be getting comfortable at 24 to 27, but you don't need a water of 4 degree from a chiller. But if you take that water also at 4 degree, you are penalizing the chiller part. So you can bifurcate this OT load and the comfort load. That should be done. Second alternative could be you can use a very small chillers next to the OT areas. So you can have a big chiller plant room at the central location, and wherever you have the OT, which is normally confined to one portion in the hospital building, there you can have a booster chiller, which can actually reduce down the chill water temperature, and you can create that circuit. So that could be done when it comes to this thing. Second thing is all the hospitals have 24/7 applications. So they are not only just like an office building or a commercial building, it's 24/7. So we have to take care of that. All the equipment should have a VFD at least into the system. So your AHU should be on variable, your pump should be on variable, cooling towers, your chillers, all should be variable rather than only one, which I normally see only the chiller is on the VFD. And we say when chiller is on VFD, everything will automatically take care, but it doesn't happen. Third, and the most important thing, which I believe it up because the 24/7 application and it's in hospital, is the cooling tower. A regular maintenance at the cooling tower gives you 2 benefits. One is it improves the efficiency of your chill water system, chiller basically. And second thing, it can avoid the situation where it can create the bacteria or something like that, which can actually harm the patient, right? So outdoor air. So both things should be considered up. I've seen a few places where the customer has gone for the closed loop cooling tower. So they don't want to bring water inside that compound. So they say, no, I can't take a risk of having this. So they put a closed loop cooling towers. They use only 10 to 15% of water as a adiabatic to the cooling tower. And they were saying that I'm okay to have more energy, more energy consumption, but I don't want to bring water. So we have to take care of the cooling tower for sure. Then variability, and if possible, we can divide two into circuits. And third thing which can be done from a hospital side is all the hospitals to maintain the OT, temperature of RH, we need heating. So over there, we can use instead of boiler, which we normally do, a gas boiler, electric boiler, whose COPs are 1, we can use heat pump, which can generate a hot water, something like 63 degree, 65 degree, or even 70 degree hot water, and simultaneously give you a cooling also. So that kind of a equipment can also be brought in, depending upon the overall application requirement, which can save not only the operation cost, but huge amount of, I would say, the infra which goes into the building, right? Because for boiler, you have an additional separate section that is required. You need makeup tanks, you need boiler, then you need power or the boiler, fuel for the boiler. So all that can be saved, and you can simply put a chiller which can generate those high living water temperature for your heating requirement, and that can sell. So these are four things which can be done from HVAC side, which actually comes to my mind.
Thank you, sir.
Yep.
Hi, Mrs. Ashish Kumar. Please go ahead with your question.
Yeah, hi, Mr. Shiv. Thank you for an excellent presentation. I have a couple of questions here. You discussed about a case study of DLF, I think, where the energy efficiency improvement was somewhere around 50%. Yes. Can you please elaborate what was the major interventions you had proposed in that particular project?
Okay. Is my screen visible?
Yes.
So there were two 180-ton water-cooled chillers associated with pumps and cooling tower, all equipped with variable frequency. So that is the one thing which was, we replaced their existing water-cooled system, which were again constant speed one. So they were replaced with the variable speed, right, and the pumps and all cooling towers. Normally, people say that cooling towers are without, constant speed because they will be running 100%, but that doesn't happen. If you have a cooling tower, it saves energy. Another thing which was done over is I think we put tube cleaning system, which is not shown here, but that was there. So that actually saves the energy overall into the during the operation.
Okay. So basically, the addition of VFDs on the chillers, cooling towers, and probably on pumps led to this 50% energy efficiency improvement.
Yes.
Okay.
Yes.
Thanks. Just again, a follow-up question on this one. See, we spoke about adding VFDs on chillers. It will, try to run chillers at part load using VFDs. So my question is, when we are doing heat load calculation or estimation, as normally I call it, it's not a calculation, it's just an estimation. So we are working at certain design conditions that solar gain, occupancy, equipment growth.
Correct.
So normally we design building, but we put a factor of diversity. It's normally people put it randomly, but it has to be carefully thought out what will be the diversity factor. So if we work on arriving at a decent diversity number based on the load profile and other aspects, probably we can install a lower capacity chiller or other equipment and probably try to run the equipment at 100% because the equipment is designed to run at 100% load. And in a way, we might not VFD, maybe, there might be instances where there is due to lower or, different ambient conditions or nighttime operation, definitely the equipment or the building will go into part load. But most of the time when it's daytime use, if we are arriving at a decent diversity factor or based on scientific calculations, then probably the need for VFDs might go away. Maybe I might be wild in my imagination, but what do you say about this?
Okay, so there are two things which I mentioned, or how I actually put it across. So first one is the diversity. So there is a very misconcept that we have the office building has a diversity of 30%, or let's say no, not 30, it's 15%. When it comes to hotel, it is 30%, right? So that's a thumb rule which we normally I have seen across people using it up, right? That is not the correct one, because every hotel, every office building is different in terms of their building itself, right? In terms of construction, in terms of material use, in terms of their location, and in terms of their usage and number of people in the building. So we can't have a thumb rule kind of a diversity. Now, how this diversity has to be calculated? So this can be calculated very easily, and it has been given in the ASHRAE 90.1, right? What it says that you calculate your 8760R calculation. So when you will calculate your 8760R hourly calculation, you can see that how many hours actually you meet the peak load. So let's say if I see in 8760R, my peak load, just 1 hour, it goes to, let's say, I'm just giving an example, 1000 tons, right? And let's say below that, I have 990 hours, 990 ton requirement for 3 hours. Then I have 960 or 900 ton requirement for something like 100 hours. And this way, I see that, okay, if I take 300 hours, top hours from the top peak requirement, that is my diversified load. For example, if I say out of 8760 hours, 300 hours, my load will be more than 900 ton. That means if I put 900 ton machine, I will not be satisfying the requirement for 300 hours in a year. Then that 900 becomes my diversified load. And this 8760 hours, when you will do the calculation for every hour, it will take care of all solar gain inside the building, all your weather profiles, right? And your internal variation in terms of occupancy. In case of hotel, this 900 might come to, let's say, 600. So if it comes to 600, that means 600 is, I can consider that as my diversified load. That is the number one. Second thing, to put VFD or not to put VFD, what I would suggest you of, when you have 8760 hours calculation done in that software, which actually generates 8760 hours calculation, which could be HAP, which could be Trace, which could be Design Builder, which could be Equist, right? Which could be any simulation software, right? You create two cases. One is with VFD, another is without VFD, right? And see the difference. If it comes that it gives you a benefit, go for it. If it doesn't come, don't go for it. It is not mandatory that you put VFD, you will get savings. That's not true, right? I'm not in favor of that. You put VFD, you will get savings. You calculate it up. You make the simulation between variable components of your chiller, pump, compressor, all with VFD. On the other side, chiller, compressor, cooling tower, all constant speed. And see the difference. If the difference is coming it up, go for it. If it is not, don't go for it. So simulation is the, I would say, the easiest way to predict and analyze. Now the question comes, how we'll do for the retrofit, because we are not doing any simulation here. So normally what we do the audit. When we do the audit, we analyze how is the building operation. So they give me the hourly, how much load the building is having, a variable load, and how much is the ambient temperature. I will get these two inputs. Then in a simulation tool, you can put a chiller circuit, which is chiller, cooling tower, pump, variable one, and constant speed one. You make out a difference. If it makes a potential case to go for a VFD, go for it. If it doesn't, don't go for it. So these are the audited programs, projects which were taken it up. So the team went there, they did the audit, and from the audit they find it out that this. And let's say when we took for the Taj one, so they put automatic tube cleaning system because they analyzed that water was very hard. It was not maintaining the good water, tube cleaning. So every 3 months they were cleaning the tubes. So what is happening? Everything is good, but if you have to see that there is a hard salt get deposited on the tubes, that means every 3 months you are cleaning the tube. That before cleaning, let's say 2 days before that, it was running underperformed, right? Because there was salt already there. Now, if I have a tube cleaning system, that salt will never deform. So that will save energy. So you have to see what is the problem and how you can handle it out. And always do simulation if it's a new project. If it's an old project, you are doing a retrofit, take the input, make a comparison sheet, and then take a decision to put VFD or not VFD. What we are saying it up, that whatever we have seen in the market, it makes sense to go with the variable speed. But still, I totally agree with you. One should actually go and analyze it for 8760 hours calculation for the new project and audit approach for the existing one, and then take a decision to put VFDs on all or only on chiller or whatever decision that has to be taken.
Thank you. Thank you so much.
Yeah.
Thank you, Mr. Ashish. Anyone else with any queries?
Yes. Hello, this is Bhaskar Natarajan, EEE. Hello, Mr. Shiv. Nice to hear you speak again. One thing in the interest of larger purpose of giving people information about these successful case studies, a company like Carrier does so many interesting, innovative projects. Is there some way by hiding the thing? Some of these things can be put in public domain so that, you know, people who want to look for information can look for it in some form, or IEEE can work with Carrier or anyone else to develop some detailed case studies, because this is extremely useful and important. So what are your thoughts on this?
I totally agree with you, and it should be done. Bureau of Energy Efficiency is doing such work already, right? But I think when they do it, it's on a complete building site, right? Not on a particular HVAC site, which is the most important. We should actually split it up into small modules, so that somebody is actually working for HVAC. They can simply go to the HVAC and they can pick up from the only HVAC. Somebody is working on lightning, they can go towards lightning part, rather than analyzing the whole building. Because when we are analyzing the whole building, we missed out the complete this thing focus. So I totally agree with you. I think definitely we can work on that part, and we can create those case studies which can be used by the larger people for the benefit.
Yeah, perhaps we should have a separate meeting. Sorry,
sure.
Someone go ahead. I'll come back later. Go ahead. I think someone else was wanting to speak.
Yeah, Mr. Abdul was there. Yeah.
Yeah, sir. This manual removing is nothing but descaling, no, sir?
Manual rescaling is nothing but descaling.
Yes.
Which we normally have a practice of descaling up once in a year during the winter time, because that's time when we are closed. But if you see, after even a use of, let's say, 1 month, your approach between the refrigerant and water goes up. And when this happens, that means inefficiency has already come into the picture. So your product, your efficiency of the chiller is gone down. And you wait for 7-8 months by the time your winter comes up, so that you can clean, because you don't get shut down, right? And in between, you don't want to do it because of another reason, which is that while you open it up and you're cleaning, if something goes wrong, let's say how you clean trap, you actually put the rod inside the tubes, right? If it punctures the main tube, then everything is gone. You have to close that tube. So you don't want to take that risk also. So you wait till the winter comes so that you can do the maintenance peacefully, and if something goes wrong, you can manage it up. But during that time, you manage with you work with the low efficiency in the chiller for next 7 to 8 months.
Thank you, sir.
Since we have no more queries, I think we can close today's question and answer session. Thank you, Mr. Shiv, and participants for this engaging discussion. If you have any more queries, please send it to dbusinesscharter@gmail.com. We can address them. Also, if your organization would like to join as a signatory of Decarbonization Business Charter, please send your interest to dbusinesscharter@gmail.com. You can find the mail ID in the chat box as well. Once again, thank you everyone for joining us. Tomorrow, same time, we shall have the session on unraveling life cycle assessment for built environments by Dr. Anne Francis, Assistant Professor from IIT Delhi. See you all tomorrow and have a good day.
Thank you, everyone.
Thank you. Thank you very much.
Thank you, sir.